We got started a handshake, how do you do, on the basics of the cell. We have now finished bonding our molecules together. We're now into some more complex, more and more complex states. Now remember, this PowerPoint has got a part 1 and a part 2. Now, the reason for that is just simply I couldn't upload, the file was too big for me to upload the whole thing. So that's the only difference between part 1 and part 2. They are all the same chapter. So just to review from last week, we're now talking about cells, and these cells all have different forms and functions. Cells can live alone, like a single cell organism, or they can come together in more and more complex configurations, like us. They have a unique genetic material. We know this is their DNA. The DNA can either be found in a nucleus or in some of our single cells. They don't have to be in a nucleus. But what the DNA is it's the blueprint for how does this cell work? How does it act in the environment? What is its job? How does it do its job? Basically, the blueprints for everything that little cell needs to know. Depending on what the cell does, we can have some pretty different looking cells. I mean, like if you think about it, actually, because I love having Zoom like this. So we could have just a plain, here we have just a plain cell with a nucleus. This could be anything. This could be a lymphocyte. Here I'm going to draw, that's a monocyte. Those are 2 of your white blood cells that help keep you safe. But look at this crazy guy I'm going to draw. That's a nerve cell. So you can see very, very different shapes depending on what their job is in your body. Our multicellular organisms, like us, we have these special cells that do work together as a community. For example, all of my nerve cells work together as my nervous system. All of my liver cells work together. And knowing how these cells function and work, that is the whole definition of anatomy and physiology. We need to know, what are they supposed to do? And that lets us know what happens if they're not doing it. That's kind of the whole idea behind studying disease, studying tissues. We have histopathology and disease management. It all comes down to as the cell doing its job. So cells have been evolving for about 3 billion years. They're not new. The primitive cells that were way back, they did not have a nucleus. They did contain genetic material, but they were known as prokaryotes, meaning before a nucleus. So they had DNA, but the DNA was just kind of loosely scattered willy-nilly. It didn't have this separate little room. It didn't have this nucleus. As the cell became more and more and more complex, the cell became bigger and bigger and bigger. Suddenly now we have the DNA is encapsulated in this nucleus. These are known as eukaryotes, or good nucleus. So it's protected, the DNA is protected in this envelope. And in our eukaryotes, we do see that they are way, way bigger. And they have all of these other structures that help them do their jobs. They have things like a cytoskeleton. They have things like organelles. I really do look at a cell very similar to the way I look at a person. A cell, a eukaryote, has skin. It has organs. It has skeleton. It has a job. It has movement. Now, what ended up happening, the theory is that because the eukaryote got so big, as it became more complex, it simply didn't have the energy reserves it needed to do what it needed to do. And so what ended up happening is prokaryote over here is like, hey, I have quite a bit of energy, and I'd be willing to share that energy with you if you would let me evolve with you and be with you. And eukaryote was like, heck yeah, no worries. And so prokaryote became what we now know as the mitochondria, the powerhouse of the cell. And this prokaryote, this mitochondria, provides the cell with the energy it needs. And the really cool thing about these prokaryotes is that they can divide by fission. So if I have my prokaryote, my mitochondria, and I'm like, oh no, I need more energy, he'll just go, on it, boss, bloop, bloop, and suddenly I have two, and then I've got double the energy. So they can be called upon by the cell to divide depending on what we need. So this next slide, I don't think you have it in yours. It's just for an interest slide. I'm not sure why you don't have it on yours. It is on my website. I'm not sure why it's not on the Moodle. So let's talk about viruses and prions for a minute. And again, you don't have to be furiously writing notes. This is just kind of interesting. How do these beings, how do these little viruses and prions, what is their comparison to our cells? So viruses are much, much smaller than our cells. And this is kind of by design. A virus has a special protein, and what this does is it kind of allows him to hide inside of our cells. So when our immune system is, on patrol looking for stranger danger, the little virus goes and wriggles in and is now hiding inside some of our cells. And the problem is that while he's doing this, he's kind of messing up the DNA, so that when that cell starts replicating, it's now replicating incorrect DNA. And in fact, what he might even be doing, they're very smart. They're changing the DNA to make it harder and harder and harder to recognize him, so that eventually he can go out into the environment and nobody even knows who he is. Nobody calls stranger danger because of the way that he's messed up the DNA, which is pretty crazy, right? That's pretty crazy that a virus can do that. Now, they can't live on their own, right? If you think about what is the virus we're all dealing with right now? Stupid COVID. And so COVID in the environment does not live very long, okay? In the air, it will only travel, 6 feet. On surfaces, depending on the surface, it may live minutes, seconds to minutes. The viruses are what we call parasitic, meaning they have to have a host in order to replicate. So, but once they do find that host, they can now start to change the DNA, and they can start replicating and then eventually take over. It's kind of terrifying, actually. Prions are these tiny little proteins. And where do we get prions from? This is kind of gross, you guys. Are you ready? Kind of gross. You get prions from eating proteins that you yourself are made of. So like if you become a cannibal and you start eating human beings, those humans are made of the same proteins that you are. And then you develop these protein-based little particles called the prions, and they basically go into your brain and they kill you. Here's an example of a prion, because who thought this was a good idea? Does everyone remember back, probably, I don't even know, you're all fetuses, so you may not even remember. There's a disease called mad cow disease. And you had to quarantine the beef. It was a big problem here in Texas because beef country. And there were entire countries that would quarantine beef if there was a case of mad cow. Well, where the holy heck did that come from? Someone thought it would be a good idea to feed cow to other cows, because we all know just how carnivorous cows are, out stomping and eating prey. So somebody said, hey, we got all this leftover cow. What are we going to do with it? Man, mix it into the feed. And the problem was then we developed this prion, and I'm going to throw a great big medical terminology out at you. Bovine spongiform encephalopathy. And basically what it is, encephalopathy is a condition or disease of the brain, the encephalus. And so these cows started developing this prion, and then we ate the cows. And then what happened? Meh, we got the prion. It also killed our brain and would kill us too. So maybe don't do that. Maybe don't feed cows to other cows, because who thought that would turn out okay? I don't know.
Can pigs get it? Because pigs sometimes eat other things.
They do. Oh, pigs are crazy.
Yeah.
Pigs, fun fact, pigs can strip a human body down past the bones to where there is nothing left in less than 5 minutes. Yeah, just look up if you have interest in that. His name is Robert Pickton, Canadian serial killer who fed all of his victims to his pigs and then slaughtered the pigs, made them into sausage, and served them to his entire town. Yeah, it's disgusting. Different animals have different susceptibilities to these prions. If a pig is on solely, constantly pig diet, then yeah, he's going to get them. But it's not like if I eat, now we've gone into the realm of bizarro land, but stay with me. If I'm like, oh, I'm going to just try it once, and I decide to try and eat a little bit of a person, it's not like, bam, I get a prion. This is something that has to happen over time. So that's where you get like if they'd only fed one cow one time, it probably wouldn't have happened. But the fact that they continued to do it, that's why we ended up with this prion spongiform encephalopathy. So can it happen? Sure, theoretically. But that's why we're careful, hopefully not to feed pigs to other pigs. But yeah, they will do some damage on a dead body for sure.
I know from watching The Incredible Dr. Pol that, like, say one has a prolapse rectum, they'll go and try and chew on it, like if there's others in there.
Yeah, pigs are, we think of pigs like Wilbur from Charlotte's Web, the sweet little Vietnamese pot-bellied pigs. Pigs are aggressive and dangerous and opportunistic and scavengers. And if one is going down, the rest will take advantage. So, heck, yeah, awful. But they taste great, so we forgive them.
So, for the sake of crazy, bizarro land.
Yes, please.
Okay, so I read into this story of this couple. They were basically really cannibalistic. They ate people all the time, and they finally got caught, and they're suspected to be known to like this cannibalistic organization. So people who eat people frequently, how would that affect them? Would it make them kind of crazy, and that's why they do these crazy things like scalp the people that they're eating and taking pictures with them?
So now you've opened up a really, really interesting bit of can of worms. And there's actually been quite a bit of study been done on this. You've now opened a realm into my fascination, which is serial killers. The initial need to eat someone is psychological. Obviously, it's not biological. And the needs stem from a ton of different things. Like if you take Dahmer, he was cannibalizing because he was just truly lonely. And he just wanted someone to not leave. And so he thought that if he cannibalized them, that they couldn't leave him. You have others like Albert Fish, who was just backcrack crazy. But it is a theory that if they are chronically cannibalistic, they can develop this prion infection, which will then predispose them to having more aggressive tendencies, more erratic tendencies, and become even more of a monster than they were before they started. So it's still in the research, right? We can't prove anything, but this is the theory behind it, that if you are cannibalistic for long enough, you will develop some sort of prion disorder that can alter your thinking process.
It's
So,
like
Do you have any thoughts on the restaurant that actually sells human flesh? Do you have any thoughts on that?
yeah, don't go there and do that, because we're not meant to eat people. We're not meant to eat other humans. And I honestly didn't think that was legal. I didn't think that you could do stuff with dead people. So
I have
I'm
no idea how they got an actual restaurant for that.
yeah, I would have to look into that, because I would have to say that that is a terrible, terrible idea. I'm just saying.
Where
What
is
about-
that restaurant?
I'm unsure, like don't quote me, but I'm pretty sure it's in California. Hold on, let me look it up real quick.
what about animals that like sharks eat other sharks? Like, what does that bother them?
So
any way?
I love this. I love this discussion right here. And this is what I was kind of hoping we wake up for a Monday. I don't think I've seen you guys this animated in quite some time. Who knew serial killer and flesh eating would be the thing to wake you up today? All right, depending on the biology of the animal will determine how susceptible it is to the prion disease. Cows are not meant to eat other cows, obviously. And so they are very susceptible. Sharks, on the other hand, are very opportunistic and cannibalistic. And that is part of them, that they are cannibalistic. So they're not as susceptible. In fact, sharks are really not susceptible to really any diseases that we know of. It's kind of crazy. They're not susceptible to cancers. They're not susceptible to different organ failures. That's why you have like 300, I think there was a shark they just found that was like 450 years old. They have no natural causes of death. And so because they are meant to be opportunistic and cannibalistic, their bodies will not. Their bodies will be resistant to the prion. A cow is not meant to eat another cow. And so because we forced it to eat another cow, then it's very, very susceptible. And so we have these varying degrees. If you take shark, which is not susceptible at all, cow, which is super, super susceptible, and then every creature is a line in between. Right? Like I said, if I eat a little bit of a person, am I going to develop? No, of course not. If a pig eats another pig, are they going to develop? No, of course not. But it really depends where they are on this line. Are they a little more closer to the shark or a little more closer to the cow? Prions.
This SpongeBob episode where it was mad snails disease.
I don't watch SpongeBob, but that, yeah.
My sister watches it, and so I gotta watch it. And it was, he got, I don't know, he got like a splinter, and he was going out, the snail was going out biting everybody. And dumb Patrick was like, well, that looks like mad snails disease, and it was turning people crazy, pretty much into zombies, and just not acting right, and people were going out, I think, biting other people, and it's a whole thing. But that's what it kind of reminded me of. I mean, just hear the mad snail disease commercial.
And all Gary had was a splinter in his tail. He didn't even have mad snail disease.
Yeah.
He had a splinter.
Yeah, I'm not a SpongeBob person, but I'll take your word for it. Now, mad cow disease will not cause you to become a zombie running around trying to eat people's brains and bite them. What it does do, however, is it eats through your brain tissue and it causes seizures, and I guess it can cause behavioral changes, but mainly more towards the dementia.
Isn't there a fungus that can infect like ants and spiders, and it makes him like a zombie, and the other ants will like chuck it out of the
Yeah, and there's
colony?
also, so we'll do one last little zombie story and then we'll go back to our cells. There is a really fascinating wasp called the jewel wasp, and they have a neurotoxin that they inject into a American brown cockroach. And they inject it right into the brain stem, and it zombifies the cockroach and doesn't kill them. It just makes them a zombie. And then the wasp will just, the cockroach is just like, good to do, okay, whatever you tell me to do. And the wasp will lead it back to its home and lay its egg and then block it in there. And then the egg will burrow, the larva will burrow into the cockroach and eat it alive from the inside until it is ready to come out of the little area that the jewel wasp has blocked it into. So, and the cockroach is just like, okay, guess you're gonna eat me now. Burr, burr, burr. and it zombifies. Yeah, that's a pretty fascinating YouTube rabbit hole you can go down right there with the jewel wasp. So there's a lot of things that can cause a zombie-like infection. Real zombies, like dead bodies coming up and rising from the dead, no, that can't happen. Biologically, that cannot happen. Cannot. 100%. All right, let me get back in here. All right. Everybody who's ever been in any kind of biology class has seen this picture. So here we have hang on, my dog needs to go out. Sorry, she's pacing around the house and it's driving me insane. All right, so right here we have the prokaryotic cell. And you can see the DNA in here that is not encapsulated. It's just willy-nilly. And don't you start. Don't you start too. Do you need to go outside too? My dogs have gone crazy. Poppy, do you need to go outside? Do you want to go outside? No, she's going to run back to the bedroom. All right, that was your one chance. Done. All right, so here we have our eukaryotic cell. Now, obviously in this picture, it looks like they're about the same size, but the prokaryote is actually about this big. It's about the size of our mitochondria. Very, very small in comparison. And this cell being so much larger, you can now see why we would need additional sources of energy. And so we have all of these tiny organs. We have, this is the endoplasmic reticulum. It acts very similar to like your liver and your kidneys. We have the nucleus, which is like your brain. We have the cytoskeleton. We have the Golgi body, which is kind of like your circulatory system moving stuff in and out. And here we have our mitochondria. And here's some others that haven't been opened. And these are what give the cell its energy. So that's the difference between prokaryotic, no nucleus, and eukaryotic, nucleus and mitochondria. So why are cells so small? I mean, in comparison, our eukaryotic cell is very, very large to our pro. But ultimately, cells are pretty small. And the reason for that is, number one, the energy limitation, right? If I had a cell the size of a rock, the number of mitochondria needed to give it its energy would not be possible. And the larger cells have trouble taking in the nutrition that they need to function, to support themselves. Smaller cells are also better governed by a single nucleus. So now, can we have cells that have more than one nucleus? Of course we can. Your cardiac cells, your muscle cells, your some of your nervous cells, they all have multi-nucleus, more than one brain to govern them. But the smaller the cell, the better all of this works. And so that's why we have these limitations on how big can a cell get. Now, don't get me wrong, there are some pretty massive cells in our bodies, but ultimately still pretty small in the great scheme of things. And no, Alex, Corona is not going to turn everyone into zombies. It is not. I would love, I used to love watching Walking Dead. I lost interest. I was one of the few that couldn't make it, couldn't do it. But it was a fabulous show in the beginning. But physiologically, if you know a little bit about how the body works, not possible to reanimate the dead. It's not possible. You have the calcium has been depleted, and without calcium, your muscles don't contract. And without muscle contraction, you have no mobility. You are not going to be running around eating stuff because the intestinal organs are some of the first to decompose. We know that zombies decompose because we've seen it in movies. Of course we have. We don't have any lung tissue, so there's no possibility that they can make any sound, because the way that we make sound is it vibrates the elastic vocal cords. Vocal cords are dead. They don't vibrate. You don't have any sound, and you don't have any air coming out of you. So if you have a dead body that can't be mobile, doesn't have a digestive system, and doesn't have a respiratory system, so much for your zombie theory.
What about the zombie deer things?
Are you talking zombie deer? Are you talking about the tick? Like the ghost?
Is that what causes them to like go almost rabid but look really gross like a zombie?
So I know that there is, I'm not so certain about deer. I believe it's the same condition, but we do have a condition specific in moose, and it's called, they're ticks. And what has happened is with global warming, the tick population does not get killed off every winter. Usually you get these major freezes, the ticks all die off. Well, now that's not happening. And so the population of the ticks has really exploded. And you get these moose and these deer who are now picking up, as they're walking through, massive infestation. We're talking 150, 250,000 ticks on a single animal. And their bloodsuckers drain them dry. And these moose and deer spend so much time trying to scratch off the ticks that they scratch all of their hair off, and you can see the gray skin because their skin now is bloodless. They've been drained. And so you see the gray skin through the coat, and they have not been eating or foraging for the winter. So they get very haggard and very thin. And you get what looks to be a staggering zombie animal, but it's actually just the ticks have gotten so crazy in population that it's drained them dry. Not zombies.
Have you heard of that fungus, I think, that affects like ants or some type of
Yeah, we
insect?
were just talking about that. And
Oh,
again, not so when I'm referring to zombie, I'm saying reanimation of the dead. That cannot happen. Can you have diseases, fungi, or other conditions that can cause an altered mental state? Of course you can. Of course, you have too many burrs. What happens? You get an altered state of mind. Are you a zombie? No, you're not. Can you reanimate the dead? No, cannot happen. Physiologically, it cannot. Can you alter a mental state to make the being complicit and compliant? Yes, absolutely, 100%.
The virus she's talking about, it's called the cordyceps virus.
It's called the what?
The cordyceps.
Wow. Okay.
Yeah, it is a real thing, and it's mostly in I think it's South America. And yeah, it does affect ants.
Yeah.
So.
Jacqueline's still stuck on a human restaurant. Oh, you guys make me giggle. All right.
It's supposedly called the cannibal.
I have a really hard time believing that they are feeding human meat, because I'm 99.99% sure That's not legal.
Me too. I have a hard time believing it too.
I have a
Oh, yeah,
really
there's a lot
hard.
of speculation around it. It's just because they made their website very sketched and weird. And then also a lot of people have attested to going and eating there. And they've attested that it's a different kind of meat. And you have to make a specific appointment. Like it's very closed. Like only certain
Yeah.
people can apparently get in.
That sounds like the most brilliant marketing scheme I've ever heard. You know, you make something super, super hard to access and everybody wants to access it. That's a brilliant marketing scheme. All right, so let's talk about the cell anatomy. I keep saying that I think of cells like little people, and they really are. They have skin, just like us. It's called the cell membrane. And just like our skin, it regulates what can penetrate and what comes out. We have the cytoplasm, which is all the stuff on the inside. That would be like my organs and my blood vessels and my skeleton. All of the stuff on the inside would be considered like the cytoplasm. And then I got my noodle, I got my nucleus, which is the genetic material telling me how to do my job, what is my role, and how do I interact with everybody around me. So the cell membrane is like the skin. The cytoplasm is all of my organs and my guts and my blood and my skeleton. And then the nucleus is like my brain. I'll give you guys a minute. Yeah, I actually have a coffee table book called Cannibalistic Serial Killers. Yeah, it's literally on my coffee table.
What was that podcast that you said you listened to? I've been looking for it, but I couldn't.
Oh, Last Podcast on the Left. It's on Spotify. So you can listen to it free on Spotify.
Very
And
punny name also.
Well, and it's supposed to be like the horror movie Last House on the Left, Last Podcast on the Left. But it's the perfect amount of brilliant research, amazing storytelling, and super dark humor. It is not for the faint of heart. So go into it well aware that, you know, if you're going to listen to something about a heavy hitter, they're going to go into some detail. And they do have what they call their gold star episodes, where if you get through it, you get an imaginary gold star. But it's pretty great. But yes, I do have a coffee table book called Cannibalistic Serial Killers. I also have the giant book of celebrity autopsies. It's a little personal insight into Miss Huff and her home.
That sounds intriguing.
It really is. It's the public accessed, because, you know, autopsies are public domain. You can go search up anybody's autopsy. And this is the big book of celebrity autopsies.
What celebrities are in there?
It's a book about this thick. So literally name a celebrity and they're probably in there. They have it from movie stars, singers, actresses, political figures. They got JFK's autopsy. They have Michael Jackson's autopsy. Oh, I mean, it's literally, seriously, a book like this thick. So it's pretty cool. We'll get through a little more of this and I'll show it to you. So here we have a picture of an animal cell, a mammalian cell. Remember, plant cells look completely different. Plant cells have a completely different makeup. They have a different function. We're looking at mammal cells. Here we have the skin of the cell is our cell membrane. Here, everything inside is our cytoplasm, and included we have our organelles, which are our tiny organs, including here the rough and smooth ER, Golgi body, our mitochondria, vacuole. And all of these tiny organs do have a function just like our organs. Vacuoles act like our stomachs. They have a digestive enzyme. We've got lysosomes, which also have a digestive enzyme, and they can bind with other things to attack and kill foreign invaders or just get rid of trash. We've got a rough and smooth ER, which works very similar to like your liver and your kidneys. We've got our Golgi body that transports stuff in and out of the cell. And then, of course, we have our nucleus that acts very similar to our brain. It kind of tells the cell what to do. We also have a cytoskeleton that we're going to talk about. So first we start with the cell membrane. This is just like our skin. It is a very flexible barrier, and it keeps stuff on the inside, and it keeps stuff on the outside. It keeps stuff from moving back and forth. And it is very, very selective and regulated as to what does it allow to move back and forth through the cell membrane. Just like our skin. Our skin will allow some stuff in, but for the most part keeps most of the stuff out. Now, just like our skin, the cell membrane is capable of self-repair to a degree, just like our skin. If I get a little cut, if I get even a larger cut, the skin can heal itself, but you can have some catastrophic wounds. And if we get damage to the cell membrane that is simply too much for it to repair, then the cell will die. We have proteins and all of these different things embedded in the cell membrane. It's not just, I know in every picture that we see, it's just like a circle. And it looks very boring, and it looks very, very just like a line. The cell membrane is an entire environment unto itself. It has proteins embedded. It has fats, cholesterols, and carbohydrates. It has little channels that will allow certain things to pass easily back and forth through. It has other proteins that help to maintain the shape of the cell. So this is not a case of it's just the line around the cell. It is incredibly complex and fluid. It kind of has this, it's called a mosaic, and it has this fluid motion that allows the cell to constantly be changing shape based on what its needs are at that time. You guys write your notes. I'm going to grab a Coke. All right. I do have a few videos on my website. I'll go ahead and link them to the Moodle as well. But just some great videos. If you want to go in, I do suggest that you go in and watch them. They're a great review and kind of go into a little bit of a deeper detail as far as cell membrane construction and what does it do. So here we have our lipid bilayer. We know here are the heads, and we know that the heads are hydrophilic, like our bison, loving a fight. And we have our tails, which are hydrophobic. They're afraid and they're on the inside. And it's the philic and phobic that governs the movement of stuff back and forth through this cell membrane. Here is the outside of the cell. It's known as extracellular or outside. Here we have the inside of the cell, the cytoplasm, and it governs the movement of stuff back and forth. Because the inside is hydrophobic. Water-based molecules have a really hard time passing and moving through because water and fats don't mix. And this is a phospholipid bilayer. So fats and, yeah, you hear her, don't you? You do know I'm teaching a class right now, right? Guru. Sorry about that. We all have pets. We all know they have their demands. She's being a little more demanding today than usual. All right, so water molecules don't pass very easily through a fat barrier. And so we do have these things like these pores and these channels and these openings that are going to help our water-based molecules a little more easily pass through. We also have things called cholesterol. Now you probably heard, oh, cholesterol is bad. Oh, I've got high cholesterol. Okay, well, this is not that cholesterol. That cholesterol does accumulate in your blood vessels and it will clog them up and cause you to stroke out. This cholesterol is good cholesterol, and it helps to wedge in between these lipid bilayer molecules and helps to give it stability. So we call it a fluid mosaic. A mosaic is something that is made of many, many other little structures, and it is fluid because it does have this constantly moving and changing shape. So now we're going to just go over and kind of do a handshake, how do you do to some of these proteins that we've got going on. We have globular proteins, functional proteins, and these proteins, you can see them all embedded here. Here we've got a protein, here's another protein that's embedded here with a carbohydrate. Here's a big channel that allows things to pass back and forth through. And these different proteins give the cell membrane its special functions based on what the job of that cell is. It will regulate what comes in and out. It will help the cell change its shape dramatically. We do have some cells that need to change their shapes very, very dramatically. We'll talk about that here in just a minute. And so these different forms of proteins are really necessary for this to happen within the cell membrane. So integral proteins, these are going to create channels that other molecules can use. A channel is just simply like a passageway. Because they may be allowing water-based molecules to move across the membrane, they're going to need energy to do that. You need energy to move water through fat. So these integral proteins help to move water-based molecules, and they do use energy. Protein channels also help to move things, but we have two categories: selective, where only certain things are allowed in, and then we have something called a pore, where you still have to be the right person, but they do allow much more free passage. The way that I look at selective channels versus pore channels is we're all going to go to a concert. Oh yeah, wouldn't that be wonderful back in the day? We all go to a concert. The pores are general admission. You have a ticket, you can get into the venue. The selective is the VIP section. You have to be a very specific molecule in order to be able to use this passageway. So the two together, pores are much more free in who they let in. You still got to have a ticket, but anybody that has a ticket can get in. Selective, only those few that have the VIP can use that passageway. So that's how I think about these channels, the selective versus the pores. Does that analogy work for everyone? Is everyone okay? Everyone's on the bus? Is anyone running to catch up with the bus at this moment?
Can you do the selective one more time? I got the pores, but
Absolutely. Selective is VIP. So the pores, as long as you've got the concert ticket, you can go in. Pores allow water molecules pretty freely to move back and forth. Selective, ooh, you got to be a special person to use this door. Only those that have the VIP ticket can use this door. And so only certain molecules can use the selective channel. You don't got the VIP ticket? Nope, this door is not opening for you. Which is exactly what it sounds like, selective. They're not letting just everybody in this door. They are being very, what? Selective. So here, look how complex this is. This blows my mind that this is each and every single cell in your body has this environment. So we have our lipid bilayer and we've got all these proteins. Look at this. We've got a giant carbohydrate, which is a sugar. Here we have a sugar and a protein bonded together. Here we have some other proteins. Here we have an integral protein. Here we have a peripheral protein. We'll talk about that here in a second. But it's just so dynamic and ever changing and moving. And it blows my mind how complex this structure really is. Peripheral proteins are called that because they're out here on the edges, like your peripheral vision. And the way that they work or what they do is they help a cell change its shape. So why is this important? Well, let's think of a cell that changes shape. A muscle cell changes shape pretty dramatically. If you all look at your muscle, we have the attachment here at our shoulder and the attachment way down here. Now, sometimes you think, oh, it attaches here at my elbow. No, it does not. It attaches way here below the elbow. That's your bicep. And when you flex, it's like I am pulling, so my string is attached here. Hello. String is attached, and when I flex, watch what happens. I'm going to pull the string, and my arm flexes. But the muscle itself has shortened by more than half and has gotten half again as wide. That's a pretty dramatic shape change. Your stomach, we're all going into Thanksgiving here soon. You're gonna gluttonize yourself. Your stomach's gonna get fuller and fuller and fuller and fuller and fuller. And those cells, just like a balloon, what happens to the surface of a balloon as you blow it up? The balloon gets bigger, but the surface gets thinner and thinner and thinner. That's exactly what happens to your stomach, to your bladder. These are receptacles that will get thinner and thinner, and these cells have to stretch and change their shapes. And it's these peripheral proteins that help them to do that.
so at what does that become dangerous? Because it's like if I'm thinking about it in perspective, like a balloon, the surface becoming thinner. If you blow it up too big, it's gonna pop.
Yep.
So at what point does that become like dangerous when you're eating?
So here's the wonderful thing about our bodies, though, if you are well, if all is going well, your stomach is getting bigger and bigger and bigger. And you have these little sensors in your stomach. You also have these little sensors in your bladder. And when it gets full, it will either, if it's your stomach, it sends a message to your brain and says, okay, no, stop eating now. And you get a feeling of being full and you stop eating optimally. Some of us keep going, but hey, eventually your stomach will go, you know what? There's way too much stuff in here and it's going to get rid of some of it. You can't eat until you throw up. Your bladder has the sensors. When it gets full of urine, it sends a sensor to your brain. Hey, we should probably go ahead and empty this out at some point soon, and you get the urge to urinate. Let's take a condition called Block-Tom disease. This is a condition that affects male cats, where they develop a plug in their urethra and they physically cannot urinate. And their bladder is just getting bigger and bigger and bigger and bigger and bigger. And the walls of the bladder are getting thinner and thinner. You can rupture it and spill all that urine into the abdominal cavity. And then that's a dead cat. That's a dead cat. So you're right, critically thinking that one right through. These organs function just like a balloon, and balloons can rupture if they get too full. So can these organs. You only have a limited amount of stretch. So how do cells recognize each other? Because we kind of want them to recognize self. I don't want my immune system going back crap crazy and start attacking me. Those are medical conditions called immune mediated, like lupus. Lupus is a condition where your immune system no longer recognizes your body and it starts attacking it like a foreign invader. Well, that's not good. So every single cell in your body has this sugar protein surface. It's called the glycocalyx. And it's unique to every single cell. And so what happens is I'm going to have, okay, each of my hands is a little cell, and the little cells come up and they kind of bump into each other. And it's kind of like, in my mind, a blind person touching your face. And they're like, okay, who are you? Who are you? Okay, yeah, you're supposed to be here. And so this glycocalyx, they recognize the outer sugar coating and say, hello, have a lovely day. Or they don't recognize it and go, stranger danger, immune system needs to get involved. And so this is how our bodies identify what is us and what is not us. And it can attack the stuff that is not us, but optimally should not be attacking the stuff that is us. And the way that it recognizes the difference is this sugar coating on the cell. So when they come in contact, they know who is friend and who is foe. I find that interesting. I find that kind of fascinating. So that's our glycocalyx, the sugar calyx coating, glycocalyx. So within this glycocalyx, we do have two families. They have two different jobs. So we have what's called the cell adhesion molecule. And basically what this is the coating is sticky. And so I have two little cells that are using the same area, the same tightrope, and they're moving towards each other. How do they continue on their way? They get sticky and they just are able to roll over each other and then go on their merry ways. This sticky coating, this CAM, cell adhesion, also helps the cells to recognize each other. And so if we have an area of infection, this CAM, the cell adhesion molecule, can signal as a beacon and get your immune system to start sending the military to come in and help with any stranger danger. As I said, the glycocalyx is also going to be for immune response. It's what targets strangers, it's what targets bacteria and viruses, but leaves your own cells alone. This is known as contact signaling. And so this is where we recognize who is supposed to be here and we target those that are not supposed to be here. So that's the whole point of our glycocalyx: identification and movement. Now, speaking of movement, we do have a couple of additional little anatomical anomalies on some cells, not every cell, but some cells. Cilia. Cilia are little hair-like extensions that move kind of like a sea anemone. And basically what they do is they take things and crowd surf them. Think about crowd surfing. A great example of where we have these cilia is in our lungs. So you get, I'm not going to use COVID because I'm tired of talking about it, allergy. You breathe in the allergy, the thing that your body goes, oh no, that is stranger danger. We should launch an attack. So the first thing that happens is you start producing mucus. And the idea is that this pollen or whatever it is in your lungs. It's already deep within your body. So our lungs start producing mucus and it sticks the foreign invader so that they can't have free access and they can't do any damage and they can't go anywhere. And now that they're stuck, what do we do with them? Well, the cilia start moving that gob of phlegm, that gob of mucus, and starts moving it out. It gets to your trachea, which is your wind tube, and the cilia go tickle, 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 and you do what? And I know it's disgusting, but yes, you swallow it. There's only two things you can do. You're going to spit it out every time? No, you're going to swallow it. But we have stomach acid. So even though we've swallowed that for what our body thinks is a foreign invader, the stomach acid is going to eat through, even if it is a foreign invader, eat through that protein coating and basically disintegrate so that they can't do any damage. And so that's the cilia, is just crowd surfing stuff, trying to move it out. Move it out. We also have cilia in our uterus, or actually in our ovaries. When the little egg is released, we have cilia that very gently crowd surf it into the area of the uterus that it's going to be implanted. Crowd surfing really is kind of the perfect analogy for that. Here, I got a picture. There's the cilia in our lungs. This cilia is what COVID destroys. That's a problem. Because what happens, and I know I said I wasn't going to talk about COVID, but hey, you know what? It's the day and the time that we live in. So this cilia, what happens is COVID gets into our lungs. Our body goes, uh-oh, stranger danger, starts producing mucus. Because we want to isolate, we want to trap that COVID. But the problem is that COVID kills the cilia. So now we have all of this mucus and all of this fluid in our lungs and no way to get it out because we don't have the sea anemone. We don't have the ability to crowd surf. That's where you end up with respiratory distress. Your lungs are filled with fluid. You can't move oxygen and carbon dioxide. You become hypoxic, low oxygen. Your pH starts to go because carbon dioxide has a different altering pH. You end up with multi-system organ failure, and then you die. And that's how a small virus attacking an isolated part of our body like our lungs can progress to something that is fatal. It's all having to do with the destruction of the cilia.
So what happens to the cilia when I don't want to say the wrong thing, but
No, there's no wrong thing. You just do it. You do you. And ask your question however you need to.
I think it's bronchitis, I guess, whenever you get bronchitis. So, and you have that mucus or in your lungs and you have that hacking cough or whatever, and you can't really breathe that well. What happens to the cilia then? If COVID destroys the cilia, then what other viruses or flus happens to the cilia then, if my question makes sense?
So no, your question makes absolute sense. So we haven't seen a virus like COVID ever before in the history. The flu does act similar, but not to the same devastating degree. Now, when you have something like bronchitis, inflammation of the bronchi, what that is, if you look here, so here's my trachea, following it down, here's my primary bronchi, and here's all the little branches. And these little branches get thinner and thinner and thinner until we have oxygen and carbon dioxide exchange. What happens with bronchitis is you get inflammation of these little tiny branches. Inflammation causes swelling. These little branches swell to the point where the openings are not, instead of having, come here, get my pen, Oh, there we go. So if, here's my trachea, my primary bronchi, and here we've got some lovely large openings. Bronchitis, these are all going to swell. So now I have my trachea, and now the openings are like this. So I don't have the same gas movement, and that's why you feel you can't breathe. That has not, and now bronchitis is itself a clinical sign, not a condition. Something has caused the airways to become inflamed and swell. It is not damaging the cilia. The reason why COVID is such a new and terrifying virus is because we've never seen anything that so quickly and so effectively completely kills the cilia. So it's not that you can't breathe because our bronchi are swollen and clamped closed. You can't breathe because your lungs are filled now with fluid and mucus and you got no way to move it out. It's all filled with fluid and mucus. And you're basically drowning. It's like a dry drowning. Does that make sense?
Oh, sorry.
No, go ahead.
Are you able to get COVID again? Basically, someone gets it.
So that is, oops, wow, time flies when we are having fun talking about COVID and zombies. So that's the other thing, is we've never seen a virus like this. And we don't know. Originally, actually I can pause this.